So I wish somebody would have told me I wasn't sharing screen. Okay. Um, okay, the the sample mean and their confidence interval 22.7 and 27.6, that is one way we can interpret this is the true population mean likely falls between 22.7 and 27.6. Okay. Or we could say we could simply say the 95% confidence interval is 22.7 to 27.6. But the interpretation is that the true population mean falls somewhere in that range. Okay. Now, the second part of the question is what is our clinic population different from the national population? And it's a slightly different question. And as we move into other types of tests, like the independent sample t-test and the pair t-test, we're more interested in comparing two different groups. And that's more typical in this kind of work, where you would compare, let's say, a treatment group to placebo in an experimental design, or you're comparing um, across different groups, you're comparing men and women. In this case, we're doing something a little different, which is we want to say, is our clinic population actually slightly, or is it different from the general population? And in this unique instance, we know from other resources, for example, because births are recorded on the age of the mother is recorded on birth certificates, we actually have a almost full census of women in the US in terms of the average age. So we can calculate that super precisely. So the question then becomes, is our clinic typical or similar to the rest of the nation? Or is it a little bit younger, a little bit older? And if so, by how much? So we're going to go back into the one sample t-test with data, just like we did before. We're going to use age as the column. Now, last time for the confidence interval, I computed it based on that sample. I'm going right back in there though. I can even just do edit. And I'm going to set up a hypothesis test. And a one sample of a hypothesis test is a little goofy in that we are telling it what we are going to compare the our sample to the known amount. And I will say that in practice, we don't do this very often, usually because we don't have a great estimate of the population on some parameter. But in this unique case of births, we do know very precisely what um, the average age is across the US. So I'm actually going to put that value in there. And we're basically saying, can tell us how likely it is that what we observe in our data would be different enough from this that it would either be would exceed chance, right? So could we could imagine, just as I said earlier, if I only took three women, let's say they were 21, 22, and 22, I just so happened those were the first three. Well, just by chance alone, with sampling three women, I could get an answer all over the place. I could have decided that it was 36 if I did happened to get a couple of older women in a row. But because I do have 30 women, we can calculate based on a t-distribution where, how much where how extreme would a mean calculation be based on 30 women to be as different as it is from what we've observed? I didn't say that very well, but let me go ahead and run this. It'll be a little clearer. Okay. So this one sample hypothesis test, which like I said, we don't do this that often, is okay, we've calculated a sample mean of 25.1. How likely is it that we would find a mean as different from 28.5 as 25.1 by chance alone. That is what our p-value tells us. It's basically a probability about the likelihood that what we're observing is due to chance. And and that we just happen to get a value of 25.16. Okay, so the p-value here is 0.0095. Our cutoff for what we consider um, a very low probability is zero point 0 less than 0.05. And that kind of just comes from scientific convention. There's nothing fully magical about 0.05. But it's the level of certainty we're allowing around our decision to say that this is different. Okay, we're allowing ourselves to be wrong roughly 5% of the time. Um, and so, yes, 25.16 is different than 28.5. Mathematically, we can say that our clinic population is 3.3 years younger than the US population. But we know that when we create an estimate based on a sample, that sample mean that we computed, it could have fluctuated quite a bit. And in fact, it could have gone anywhere between 22.7 and 27.6 based on the confidence interval. It was just as likely, given our data, to get means calculated in this range. So this p-value is saying, yeah, this difference between 28.5 and 25.1 suggests that our clinic population is, in fact, different, in this case, younger than the national average. Okay. This is, it's very unlikely that we would get an answer of 25.16 that far different from the 28.5 just by chance alone. Okay, it's probably a real difference from the population. Okay, so I know it's definitely a leap in the logic of statistical thinking, but this is why we draw samples. This is why we do studies based on samples. And, normally in the real world, we are using larger samples than this, and we probably would get more precision, and we can be even more confident in our conclusions as we got larger samples. But especially if we're trying to have fewer participants, let's say there's some burden or it's expensive, we try to keep studies as small as we can for those reasons, especially if there's some sort of intervention being happening. So we can't, just have infinite sample size or as big as we'd want sometimes. Okay. So that's all we're doing in this first problem is basically setting up this test to see if our clinic population is different from the population as a whole. Okay, and we're doing, again, just as review, we're doing both of those within the t distribution table. You'll notice here there's a z-stat table. Technically, as we get sample sizes closer to, let's say, 100, 120, uh, and higher, the t distribution, which is shaped kind of like this, or it even for small samples, it's even flatter. I'm not doing a very good job with my fingers here. Okay, so the t distribution is actually not a single distribution. It's a series of distributions that become more like a normal distribution as your sample size gets larger, and eventually it becomes what's called a standard normal distribution or a z distribution. And so the z-stats you're going to be able to do basically the same statistics. You'll notice that it even has the exact same options, but it's mathematically a little different because it's always going to default to a kind of a standard confidence interval width, uh, which mathematically is if you look at a t-distribution table, you'll notice that the value of the t-statistic, as you get much larger samples, it doesn't change that much. And so your the effective sample size starts to become a little less as you get um, larger and larger samples. Okay. But we're going to stick with doing the t-test. You actually get the same answer if you, it's smart enough to know based on the sample size. Okay. So that was actually problem one in a nutshell. Um, and I want to go ahead and move on to, like I said, last time I kind of had to, I wanted to make sure that I got through all of the different um, pieces, parts of the assignment. Module one, module two, there we go. Okay. And that's why we're calling this now inferential statistics. And I do hope you will watch the lessons because I'm a little more articulate when I have a script. It's a little more pre-planned, but it goes over all of this and more. And not till lesson 8 do we even talk about t-tests. Okay. And then likewise in StatCrunch tutorials, you have how to do confidence interval for mean, how to tell the difference between two means, uh, pair data, which comes up in our thing. Okay. I don't think there's a lesson here on one sample t-test. Okay. All right. So analyzing data. Oh, I forgot to mention that problem also has you compute a 99% confidence interval. You're going to use the same uh, procedure here. I'm just going to click on edit, and you can actually do all three things within the same. I'm just going to change the width of the confidence interval here to 99. Right. In standard scientific literature, you're going to see a 95% confidence interval most of the time. It would be very unusual to see somebody present a 99% confidence interval, but this is mostly for demonstration purposes that if I want to have more confidence in where the true population mean falls, it's actually going to compute a slightly wider confidence interval. Instead of 22.7 and 27.6, it widens out to 21.8 and 28.4. Might be a little counterintuitive. You're like, well, we just did a higher number, 99. What this is saying is now we can be 99% sure that the true mean of the population falls somewhere between 21.8 and 28.4. We can be all the more assured that this range captures where the true mean is, okay? And so that's the standard allows for a little more room for error, room for making an inference error. It's a little less conservative, you could say, from a statistical standpoint. But it also happens to be the convention across numerous scientific publications, including JAMA and your really good journals and stuff. They still have stuck with this 95% confidence intervals and p-values less than 5. It's just kind of how science has evolved. Not a perfect system by any means. Okay, so that should be a wrap on problem one. If there's any further need for discussion on that one, I'm happy to go back to that. Okay, so let's go on to the next one. Okay, and I did want to show that the assignment data is all in that Excel file that I put in announcements, and so it's going to get a lot easier for you to cut and paste into. So this one I did was problem two. I'm sorry, week two, problem one. And I had all the ages right there, and so I copied and pasted from there. It just makes it cleaner. I know from this one they were in two columns, and it may have given you some trouble. Okay, so problem two, we have um, this is a more typical scenario where we're comparing two different groups on some outcome. Okay, the last one we were comparing a single group to some known value. Usually in a study, we have some sort of comparison group, right? And if we were to look at the different study designs, clinical trials, randomized trials, um, observational studies, usually there's something that we're trying to compare. Somebody who's exposed, who's not exposed, someone who has a disease, who doesn't have a disease. And that's exactly what we're looking at here is women who have hypertension and women who don't have hypertension. And we want to see if the birth weights of their infants are um, different. Okay. So I'm going to go ahead and copy this data, knowing this is for the next problem. And it should faithfully, if you want a new data set in StatCrunch, you're going to want to go to StatCrunch, new data table. And if you think you're going to go back to an assignment or back to a question, be sure to save that data set first, because then you don't have to re-enter all that data. I mean, it wasn't that much last time, but okay. So this is my data for problem two, and let me go ahead and read the narrative aloud. Oops. Oops, that's not what I wanted. I don't like screens, by the way. I don't like how small they are. Okay. So this is our birth weight data, problem two. Okay, and this is from a case control study. And a case control study, what you do is you take a bunch of people who have a condition and you try to come up with a reasonable control group to match them. And that can be very challenging. Let's say we were doing a case control study of Alzheimer's disease. What we'd want to get is someone who's a similar age, comes from a similar neighborhood or similar background, but the difference being they don't have Alzheimer's disease, right? So that's how we would set up a study. And then we retrospectively ask questions or we compare them with respect to um, different other measures. This is a little different because we're taking women who have hypertension versus not hypertension, and we're actually more interested in what is happening with their neonates. Um, so two samples of 15 mothers with and without a diagnosis of hypertension were randomly selected from electronic health records among mothers who gave birth on the same date. Um, you could actually think of this as a cohort study now that I think about it, because you're really thinking of it, you're thinking of hypertension of the mother as being the exposure, but that's you don't really need to know that for the purposes of doing this, and our interpretation will be the same. But okay, so yeah, technically this is a case control study of hypertension, looking at low birth weight as an outcome, or cohort study. Anyhow, perform an independent sample t-test comparing birth weights of neonates among mothers with and without hypertension. So what you have in your table is the birth weights in grams. So if you thought these were crazy weights, that's how they usually weigh newborns. Okay. And so these are grams. We have a pretty small sample here, 15 in each group. Okay. And now we're going to test and look at whether there seems to be any kind of difference between the birth weights of these two groups, right? And like I was saying with the pregnant women and their ages, we're not just interested in these 30 women. We want to be able to say something about a larger population, uh, and we don't always specify what that larger population is. We're at least thinking about our clinic. But here we're actually trying to say something maybe even bigger than that, is that women who have hypertension versus those who don't. So based on basically all pregnant women, does hypertension seem to be a risk factor for having either a low or high birth weight baby. We haven't really specified what direction we think that would go into, whether they be um, heavier or lighter. And probably clinically it'd be more meaningful to use some sort of cut point to say low birth weight or something like that. But we're just um, testing here for the purposes of an exercise. So in this case, I'm not going to do a one sample t-test. I'm going to do a two sample. But let me go back to the homework actual narrative to make sure that we cover everything that we want to accomplish in problem two. So perform an independent sample t-test comparing birth weights of neonates among mothers with and without hypertension. We're also going to compute a 95% confidence interval for the difference in mean birth weight of neonates among mothers with and without hypertension. Okay, so we can actually do both of those things with the same procedure in the T statistic thing. Just like we were able to do a confidence interval and a one sample t-test, we can actually do that right here. And you can see there's two different tasks we can perform. There's a hypothesis test and there's a confidence interval for the difference between the two means. I'm going to do it in the order that uh, it was in the problem. And in this case, we're going to say our values of, I'm going to go ahead and put the with hypertension as group one. Doesn't really matter which one we put. The the reason why it might matter is we're subtracting one from the other when we calculate the difference in means. And we have to keep that in mind when we look at what the difference is. Okay, so let's go ahead and compute that. And again, we're doing what's called a t-test um, for the difference between two means. And okay, so we're subtracting mean 2 from mean 1. So we're subtracting the no hypertension from the with hypertension. So a positive value means that the, let me make sure I get the logic right on this because this can be a little tricky. 3, 5, 5, so with hypertension. Yeah, okay. So the with hypertension group is actually slightly heavier than the no hypertension group because I'm subtract this is the difference. And so this minus this is a positive value. So the birth weights of the um, neonates are actually a little bit heavier for the mothers who have hypertension. However, if we look at the p-value of this hypothesis test, it's 0.1657. So yes, we calculate a difference here. It appears that the difference on average is 507 grams. But statistically, we cannot conclude based on this data that there's a difference between the birth weights of those with hypertension with those without hypertension. Okay. And what this is saying is we could have had a difference as large as 507 grams just by chance alone. Okay, and you can see there's quite a bit of variability here in the birth weights. The lowest, this is very light, 595 grams. I'm just eyeballing it here. The highest one looks like 4,111. Okay, and so there's a lot of variability in birth weights. And, and so a value of 507 might sound like a lot, but actually it could be actually be clinically meaningful. However, it's not statistically significant. And what that means is we could have had differences as large as 507 just by chance alone. If we would have continued sampling and we could have had differences as big as this. Let's say we took a totally different group of 15 women in each group. We could find differences as large as this in the complete opposite direction. It could be 507 grams lighter. there's nothing to suggest here that this difference that we calculated is statistically significant. It doesn't hold up because it's not large enough to suggest that we couldn't have had that by chance. And it's actually the t statistic itself, which we don't ask you to calculate, is really a simple calculation. The the sample difference divided by the standard error, right? And so it's basically there's enough variability here in the data that this difference could have had to happen by chance. So even though we calculated a difference, this difference is not statistically significant. And the way we set up a hypothesis test is kind of goofy. It's you can think of it as like innocent until proven guilty. We need enough evidence of a difference to conclude that there is a difference. And 507 as a difference isn't going to cut it for a sample size this small. We would have needed to observe a much bigger difference in this sample size to conclude that it was not due to chance. And so if I was really interested in this question, does hypertension impact birth weight? I'm going to need a bigger sample if I really think that there is a difference. But based on this, there's not enough evidence to conclude that there's a meaningful difference. Okay. So if I go into options, I can also go straight to computing a confidence interval for the difference in the means. And it's a very similar thing that we're doing, and I'll show you. Okay. We're now just, it's a slightly different way of looking at this question. And when we look at the confidence interval for the difference, the confidence interval for the difference falls between negative 224 and positive 120, 1,238. So this actually has more information than a p-value, and it's saying the true population difference between these two groups, based on our sample here, could be anywhere from a negative difference, meaning the with hypertension are a little bit lighter than those without hypertension, or they could be 1,200 grams heavier. But this is very similar to the conclusion that we drew from the hypothesis test, which is we can't say whether they're heavier or lighter. There's not enough evidence. We can't be confident enough that there's a difference based on this sample size. Okay, and remember what I said about sample sizes is that as they get larger, your confidence intervals are going to get narrower. Likewise, as we increase our sample size, the more likely any difference that we do detect could be statistically significant. And this gets into when we think about study design, how big of a sample would we need to detect a difference between two groups? That's what we call that power calculation. But it's basically part of the study design to say, okay, well, we know there's this much variability. How big would the study have to be, knowing that there's this variability to detect a difference? And so based on this analysis, we're coming to a very similar conclusion that because the confidence interval overlaps zero, meaning it could be negative, it could be positive, it it could go either way. So we're not going to say that yes, one's different than the other. Even though if we were just to blindly compare the two means, we could say, oh yeah, women with hypertension have babies that are 507 grams heavier than those who don't. Well, could or that could just be just a random sampling error. And we don't want to make an inference about a population based on this information because we just don't have enough data. This difference isn't big enough, okay? So it's really tempting to come to some sort of conclusion based on just calculated difference. But what we want to know is how likely is this to hold up? And it's not. It's not the very big difference. Okay. So just like the previous problem, you can do everything you need within the analytic steps um, within the same dialog box. In this case, a two sample t-test. I keep bringing up the wrong documents. I really need someone to hold papers for me here. All right. So let me go to the interpretation here. So I showed you how to perform it, right? The analytic steps. But what I want to spend a little time here is this stating of the null hypothesis for the t-test with specific mention of the outcome of interest and the two comparison groups, okay? So when we're stating a null hypothesis, we're basically formally stating that there is actually no difference between the two groups. And you might think, well, that's not what I'm interested in. I'm interested in there being a difference. Why else would I study this? But the null hypothesis, the way we set this up is totally backwards. But it's that whole sort of innocent till proven guilty. We want to see that we have enough evidence to suggest that the null hypothesis of no difference is not very likely to be true. I can say that 6 times and it's going to sound a little weird. This is where hypothesis testing trips up everybody. So when we state the null hypothesis, it's always going to be that there's no difference. Okay. That's what we're formally testing with our statistics. Is it how likely is it that there's no difference, basically, based on what we observed in our data. Okay. And so the null hypothesis, whether we're doing a t-test when we get to ANOVA, whether we are doing linear regression, correlation, you can really think of it as no difference, no association. Okay. The proportions in a 2 by 2 table are the same. We set it up that way. It's allowing us our statistics to be a little more conservative, that we need enough evidence to suggest otherwise. And that's what the p-value tells us, is whether we should reject the null hypothesis. Do we have enough data? Is our difference that we're observing big enough to suggest that the null hypothesis is very unlikely to be true? Okay, so it takes a ton of practice to get your head around this concept. I know it did for me when I first took statistics. I'm like, well, that's just backwards. But it is set up that way so that we can avoid making too many errors in inference. It's a conservative way of doing it, just like with jurisprudence, where you don't want it to be proven guilty without enough evidence. We need enough of a difference between two groups to suggest that there actually is a difference in the overall population. Um, the interpretation of a confidence interval, which is the second part, is very similar to how we interpret any kind of confidence interval. It's just saying that we think in the true population that the difference in this case falls somewhere between this value and that value, the other value. In this case, we had a negative value and a positive value. So it could be negative, it could be positive. We can't really say. But it's very similar to when we calculated an age confidence interval. We're saying that the true population age is somewhere between 22 and 28 or whatever it was. We're saying the difference, the confidence interval of the difference, is that the difference could be negative, it could be positive, it falls somewhere in this range. And so really all you have to do is say that, you know, interpret it in terms of the low and the high value. And I would add to that because it does the confidence interval includes zero, we cannot conclude whether there's a negative or a positive difference. Okay. And then provide a conclusion regarding group differences based on your hypothesis test, stating whether or not you reject the null hypothesis. Describe the 95% confidence interval for the difference in group means, including the lower and upper limits. Does this to change your interpretation of the results of the t-test? I kind of went over that already, which is basically you're you're coming to the same conclusions between using a t-test and using confidence intervals around a difference in two means. It's two ways of looking at the same problem. The confidence interval actually has more information in it than a t-test does. The t-test is cut and dry. We say if it's less than 0.05 for your computed p-value, then it's statistically significant. And all we can say is there's some difference. Okay. In this case, there wasn't a difference. But we're saying if it was less than 0.05, there is likely to be a difference. In this case, we said we don't have enough information to conclude there's a difference. We're going to say that there's no difference. The confidence interval actually provides a little more information. It says the true difference is somewhere in here, in that range. But we're still going to come to the same conclusion, which is it could be negative, it could be positive. Okay? It's just it tells us kind of the range. So it's a little more informative, which is kind of strange because in the scientific literature, you're going to see p-values reported more often than confidence intervals. And there was a big movement to use confidence intervals instead of p-values because they do have more information. Often you'll see both, even if there's some redundancy in that. Okay, problem three. And like I said, I can come back to any of these if there's questions. I just want to get through this all. Problem three, a researcher is interested in estimating the prevalence of type 2 diabetes in their county, etc. The big difference here is the setup. We're going to compute the estimated prevalence of type 2 diabetes and a confidence interval around a proportion. The thing that's different here is how our data is set up. And what we have here is almost like the results from a frequency table, right? So if we had observations, we'd have 45 records saying yes, we'd have 467 records saying no, and we'd have 8 records that say don't know, okay? Which is a totally different way of seeing our data, but we can actually calculate statistics based on already existing counted up data. It's kind of cool, I guess. We don't need the raw data to make some conclusions or to develop some confidence intervals around them. Um, and StatCrunch allows us to use data in this format by using the with summary. Data proportion statistics, one sample with data. Okay. So, oops. Oh, I'm sorry. I didn't put my data in. That's why. Oh, sorry. I totally said not that. Not with data. Proportion, one sample with summary. Okay. Summary is when we already have basically created a frequency table. We're not going to do this again, I promise. It's a little confusing, but we're going from our already aggregated data. Otherwise, you'd have to enter yes 54 times or whatever it was, no 400 times, and don't know. Okay, so we're starting from like our table, our frequency table. But we can use the with summary, and here's how to do it. We're going to put our yeses here and our nos here. Oh, no, I'm sorry. Our yeses here and our total number of observations here. Basically, whatever we're interested in, we're calling it a success. And our number of observations is our number of observations. It's kind of strange language. Success just means, let's say we're flipping a coin and we're saying heads is a success and tails is not. It's how many times. It's actually kind of archaic language. I don't know why StatCrunch uses that language, to be honest. But basically, we're going to say how many yeses, how many out of the how many total, okay? And I know that seems really screwy because why not just put the no's in there? Um, So if I go to my assignment, in the assignment we said we're going to go ahead and consider the don't knows as knows. The idea being, if you're told you have type 2 diabetes, you probably know whether you do or not. Could be wrong about that, but pretty sure. And that's just the decision we're making. Okay, but in any case, our number of successes, we're going to say the number who do have type 1 diabetes or type 2 diabetes, we're going to say 45. Everybody else is a no, so we add all those up. Let's see, we're at 512, 520 total. Just doing the quick math on the summary of all those. Okay. And then just like before, we can do a confidence interval for the portion. We get here the sample proportion. This is the prevalence estimate. This is how basically how many people were type 2 diabetic, 8.6 some percent. And then we have a lower confidence interval and an upper confidence interval saying that in the true population, the estimated proportion who are type 2 diabetes would fall somewhere between 6.2 and 11%. Okay, so these are proportions, just multiplying by 100, you get the percentage, right? So you could state it in proportions. I find it easier to think in terms of percentages. So you have 8.6% of the population are type 2 diabetic, and the low end would be 6.2%, the high end would be 11.1%. Okay. So this is a little tricky how the data is set up, but confidence intervals for proportions are very similar to how you interpret a confidence interval for a mean. You're saying the true population proportion is somewhere between 6.2% and 11.1%. And the formula for a confidence interval for a proportion is actually a little different, and you don't need to know that for the purposes of doing this. But proportions, you actually need a slightly larger population to get precision around a proportion, just because it's a yes/no kind of answer. Think about something like age. You could have all these different values, right? But for diabetes, it's either a yes or it's a no. And so you actually end up needing mathematically a larger sample to get a narrower confidence interval. And it's similar to what I was saying in the early part of the course, where the level of measurement does matter. And it also, think a yes no response is a categorical response, right? Yes versus no. You have less information than you do when you have something like an interval measure. Okay, so if we were to take their A1C levels or something else where we had to continue, then we could probably get away with a smaller sample size. But for proportions, and again, you don't need to know that. We're not having you hand compute a confidence interval, but just know that you tend to need a larger sample size to get a tighter confidence interval compared to when you have more information. Okay, but you don't need to just know that for the purposes of this problem. Uh, so you're going to get the estimated prevalence and the confidence interval all with that one procedure. Okay. Um, and that's pretty straightforward, actually. The tricky part is knowing that you're using it from summary data. Okay. And the last part of the interpreting results is kind of goofy. It says, explain if the analytical decision to use a response as don't know as no would have substantially changed the prevalence estimate or the confidence intervals. You could formally test that. You could go back in and um, enter, just exclude the don't knows, right? You could just, and see how much that affects things. Um, or you could say, well, as a proportion of the whole, or where's the problem? These 8 responses is probably not going to change my estimate by that much. You wouldn't necessarily know that though. But it's a very small percentage of the total. So and especially because our confidence interval rounding decimals, it's probably not gonna make a huge difference. Let's go ahead and see what it would make. So I said, what did I say last time? I can go, actually, I can go right into edit mode. Instead of 520, I'm gonna say 512. We're just gonna exclude the don't knows. And you can see just by observation, 0.87%, confidence interval 6.3 to 11.2. What was before? I don't have it. Pretty close. Okay. So, and especially our confidence interval, we're already saying that the true population proportion is kind of somewhere in this range. It's not going to hugely affect the precision of our estimate. Okay. I forget what it was. It was this, I'm just gonna remember it now. 8.7% versus 8 point if, with rounding, 8.7%. So it doesn't make really that big a difference. And the whole point of that is really to say, like, we're making an analytic decision to assume that the don't knows are actually knows, that they don't have type 2 diabetes. And what we're doing, we call it a sensitivity analysis. How sensitive are our results to the decisions that we make analytically? And those kinds of things do come up where we have to, data isn't always perfect. We sometimes get data that is, we had to make a decision because there were some people who said, I don't know if I have type 2 diabetes. And we could just throw them away. We could include them. So we're really just saying, oh, and if there was a huge difference, we might want to mention that. Like if we were writing this up in an article, it's like, this is how we chose analytically to do it, but if we did this or that. But you don't see that done that often in the, yeah, although people should, because sometimes your decisions that you make can have an impact on the analysis. All right. Moving ahead, moving right along. My favorite movie, The Muppet Movie. Moving right along. Okay. Problem four. This is um, this is similar to problem two in that we have two observations. Oh, I'm sorry, we're doing a t-test, but this one is a little different because these are the same people measured twice. Okay. You could think of this as pre-test, post-test, as a study design. But here there was an intervention in between. They received physical therapy. And notice the data is set up very similarly to how we had two different groups. This is a little more traditional where we have each row represents a case. So this is their baseline score. This is their follow-up score. So this person went from 30 to 50. So this was a shoulder. They went from being able to move it 30% to being able to move it 50%. So they improved a little bit. I know this because I had frozen shoulder recently and we were trying to improve my range of motion. It happened after a ski accident. I broke my collarbone and after it healed, then because I held my shoulder in one position for so long, it froze. Don't recommend it. Um, okay, so yeah, range of motion, important in PT. So 50% at follow-up, the next one, 28. Okay, so it looks like folks are improving a little bit. That's good. But don't, these are the same people. The important thing here, okay? And it looks like if we go down here, this guy has improved from 23 to 48. Good for them. This person a little less. This guy actually went down a little. Oh, this one went down a little bit too. Okay. But most of them, it's like, okay. So, but the point is, these are the same people. we can't run an independent sample t-test because these are not independently sampled people. The independent sample part has to do with they're different people. They're different. There's no dependency among those people. And ideally, when we do even like a random survey, we don't want people from the same household to respond because they're probably more similar to the person we got the answer from than they would be from some other randomly selected individual. So if you were to actually participate in a like a phone survey or something like that, they they wouldn't say, "Oh yeah, well while we're at it, let's just talk to everybody in the house and get their opinion." Um, that's a little different because the clustering is around family members being more similar. But obviously, people, when we're measuring them twice, are more similar to themselves than they are other patients. And so we have to account for that in our statistics. And it's really answering a different kind of question too, which is are they different at follow-up than they were at baseline? Okay. So again, the setup is very similar. I know from experience that title, it's not going to like that percentage sign, so I'm going to just copy the data. Please tell me I didn't close. Did I close that cron accidentally? I'm very good at doing that kind of thing. It's like I might have. Let's see. Oh no, I didn't. Okay, cool. I drive myself crazy when I. Okay, so I'm gonna go stack crunch, new data table, Control V. And I did that because I know that it's not gonna like this percentage signs. So I'm gonna say baseline. Follow its range of motion. Okay. So the difference here is when we run the statistics, we're still going to use t-stat. We're still doing two sample. Oh no, I'm sorry. Oh, no, we're doing paired. Some stats programs, you just check a box within the two sample and say that it's paired as opposed to independent. They actually have a separate paired option. Sorry. Sample one, we're going to say baseline and follow up. Now we have to be careful here because when we subtract the difference between their baseline and their follow-up, it's going to be baseline minus follow-up. If we're thinking that they're going to improve, hopefully their follow-up range of motion would be higher than their baseline follow-up. That would give us a positive value. If they didn't improve, it would be a negative value. So it does not actually matter how you set this up. We're just comparing baseline to follow-up. I'll show you here in a second why it might matter. But I'm going to run a paired t-test here. And again, once again, we have two different things we can do within the same procedure. We have a t-test and we have a confidence interval. I'm going to go ahead and do the t-test. And, okay, so it's baseline minus follow-up. So this can be a little tricky if you're like, oh, they actually went down by 9 points. No, they actually improved by 9 points because we took their baseline score, we subtracted their follow-up score, giving us a negative value, meaning the follow-up score is bigger than the baseline score. To me, that's very confusing when I'm looking at it because I'm thinking, what, they went down 9 points? No, they didn't go down point. They actually they improved by 9 points. That would be terrible if you paid all that money for PT and it actually got worse. Um, okay, so the reason I'm choosing it this way is I want the difference to be stated as a positive difference. That's not changing anything about the data. It's just, it's going to help me interpret it a little better. Just got to be careful thinking about what subtracting one from the other is. Okay, so now it's follow-up minus baseline. So the follow-up value is greater than the baseline value. By how much? It's 9, 9, 9% range of motion. And so let's say here, after 2 weeks, It's not very much change, but we'll give it to them. They got some improvement, okay? And more importantly, we can say, oh, I shouldn't say more importantly, we can we can conclude here that the PT did something, okay, based on the p-value. Because our p-value for this test suggests that it's, first of all, it's less than 0.05. The difference that we're seeing here of 9% range of motion is statistically significant, meaning we would not expect to get a difference as great as 9 um, points average improvement based on chance alone. It wasn't just that they were having a bad day in the one case and something else, and there's some random reason why there was improvement. Like there seems to be some improvement. It might not be a lot, and even our calculated difference is not clinically very much. We still statistically can also conclude that there is at least some improvement. Okay, and again, the null hypothesis that we set up in a test like this is um, that there's no difference. And you can even see that in the output here. It says mean difference equals the mean of one group minus the mean of the other. And the null hypothesis is that that difference is 0. Okay, I should have pointed that out all along. The null hypothesis says the difference between the two groups is 0. The p-value tells us how likely the null hypothesis is to be true, that there's no difference. In this case, there's only a 1.2%. Where do I get a percent? Because I'm converting a proportion to a percentage. A 1.2% chance that the null hypothesis of no difference is true. So we can reject that based on our convention of saying if it's less than 0.05, we're going to go ahead and say, nope, the null hypothesis of no difference does not seem to be very likely to be true. We reject the null hypothesis. We think we conclude that there is a difference. And formally, that's the alternative hypothesis that the difference between the two means is not 0. Okay, and notice this is not saying which direction the difference is. We can see that they're higher at they improved in the range of motion, but formally speaking, this is really just saying that the difference that we're observing is big enough to conclude that it's not 0. Okay. Um, and this kind of sets up what the last part of the homework talks about, which is, well, what if we set this up as a one-directional test? Because a, a typical hypothesis test actually allows you to detect both a positive difference and a negative difference. It could be super better, it could be super worse. And ethically speaking, it's probably better to set up tests that way. Though I love my PT person because they rescued my shoulder, they could have done worse, right? They could have squeezed so hard that they made my range of motion worse. There are certainly are interventions that can make things worse. So a two-sided t-test would allow for the difference to go in either direction. We could have seen a negative change after 2 weeks. In case of frozen shoulder, it's very actually possible that you could because it's just continuing to freeze, which is what I had. But in any case, we normally set up tests as two-tailed, but we can put all our statistical power, all of our ability to detect differences all in one direction. We're only interested in improvement. We don't care if they decline. And this is kind of a nuanced thing. Sometimes they do this in clinical trials where they really want to detect a difference between the new drug and the old drug. They'll bank all their power into the detecting a difference in the positive direction, there's some there's some ethical reasons why you shouldn't do that. You should allow for differences to go in both directions. But that's what the whole point of the second part of the question is. Basically, repeat the statistical, and I showed you you can get a confidence interval for the mean. I'll do that also. But we're going to repeat it doing a one-tailed test for a difference in an improvement in range of motion only. Um, Let me do the confidence interval first. I can just edit. Obviously, you're going to want to save both, but confidence interval. Remember that we did say that there was some difference. The confidence interval around the difference, which is 9.09, is 2.45 to 15.72. So this actually gives us more information, right? It's saying the true difference in um, range of motion is going to fall somewhere between 2.4 and 15.7. And the person who's all excited that there was improvement might be a little tempered by the fact that, yeah, there was some improvement and it was statistically significant, but it could have been as low as only a 2% improvement. Uh, and it could have been as big as 15%. And you're like, well, wait, it wasn't. It was 9%. Well, what we're trying to do here is say, knowing that there could be this fluctuation within our data, and we're doing this based on a sample for which we're trying to make inferences to a larger population. Given the fact that we only have 11 people in each group, I'm sorry, 11 people total with two observations each, we can't be super confident of where that, and this confidence interval suggests kind of minuscule difference. It's statistically significant, whether it's clinically significant, different question entirely. It seems like they are improving a little bit. Is it worth the $90 to $120 a visit? I don't know. Maybe, probably. Hopefully they'll get even better range of motion after a little while. Okay. But that's not what we're doing with statistics. We're just making decisions based on the data. Okay, so that's all that was. So that's the confidence interval. And then this question of directionality. Okay, so if we wanted to bank all of our power, especially since we have a very small sample here, and we're really confident that, I shouldn't say confident, we're really only interested in um, going in one direction. When I go back to hypothesis test, instead of saying that the alternative hypothesis could go either way, that it's simply not zero difference, we could say we're only interested in if it's positive, that it's greater than zero. In practice, this comes up very infrequently in the literature. There's, like I said, there's ethical reasons because you might want to allow for to go either way. What this does is it just creates a little more statistical power because we're not even allowing for errors of inference in the other direction. It basically cuts it in half. Um, and this is more of a mathematical thing than anything that you don't have to worry about. But notice if I do this, I get the same mean. I get a slightly lower p-value. I'm not going to come to a different conclusion, but let's say that that previous one was kind of on the cusp. It's a slightly higher powered test. A difference as small as 9, all in one direction. I don't want you to get too confused by this because this is a little confusing. But basically you can get a minuscule bit more statistical power to detect a meaningful difference if you only put it in one direction. I don't recommend it, but that's we're just showing you all the possibilities here. So that's what that's all about. Um, okay. So let me go back to the interpretation real quick. I covered everything. Okay, so a little bit here in the interpreting results, it says explain how a one-tailed test might be appropriate for this intervention and which direction you would test for a difference. Would your conclusions be different based on a one-tailed versus a two-tailed test? So we ran both a one-tailed and a two-tailed test. We saw that the p-values were the same, but this is more like what would you, where would you put your money? Like, are you betting on it being an improvement? Are you betting on it being not an improvement? This is sort of a logical question. Um, okay. And then again, stating the null hypothesis always is going to be that there's no difference. In this case, I want you to say a little more than just there's no difference. You're going to say the difference between baseline and follow-up is the null hypothesis, there's no difference between baseline and follow-up. Range of motion, if you want to be even more specific. Okay. And that's going to be true of all the statistical tests that we do. When we get to correlation, we're going to say that there's no correlation. If we're doing a test around correlation, if we're saying a linear regression, we're going to say the slope of the line is 0. It's always going to be nothing. And null, the word null comes from some similar origin as no and nothing. So null. In fact, I think in the UK and Canada, like null, nil, null, 0, nothing. Um, so that's what that means. And it's a little counterintuitive, but that's how we do statistics. Yay. All right. I have once again miraculously left a full 3 minutes for questions, but for those in attendance, any quick little questions about the homework? Okay, going once, going twice. I do really appreciate everyone who's tuned in. I realize this is a lot to digest. I hope it's becoming clearer. If not, practice, practice, practice. This is the biggest leap we're making in terms of um, kind of the logic of doing statistical analysis. So hopefully this helped. You all have a good night and have a good dinner. Good night.